Okay, so okay. On Monday, we start looking at the fermionic gas. So these were our basic equations, which told us the first one is how we can compute mu from the given number of particles. The second one gives us the total energy. The third one gives us the pressure. And at least on Monday, what we did was we looked at what happens when z, which is e to power beta mu, is close to 0. We had first seen that z close to 0 means it's n lambda cubed is small. That is a rarefied gas, which makes n small at high temperatures, which makes the thermal wavelength small. So at high temperatures, we calculated how these various quantities change. So this is an exact relation we have. This n lambda cubed over g being the degeneracy is equal to this function f 3 to 3 halves z. And these three are the general results. And we looked at what happens at z close to 0. And we had seen that when you look at the pressure, we calculated the first correction to the pressure. And we had seen that the pressure is slightly larger than what we call the ideal gas, the Maxwell-Boltzmann ideal gas, the classical ideal gas. The classical ideal gas just gives us PV is equal to NKT. And then we looked at what happens strictly at t equal to 0. The first thing we observed was the Fermi-Dirac distribution, which gives us the occupation number of states, just becomes a step function. It is 1 below an energy value and 0 above. So basically at t equal to 0, all the particles go to the ground state. But since they are to the lowest possible state, let's say, but since these are fermions, not all of them can go to the ground state. Once the ground state is filled, the next electrons go to the first excited state, second excited state, and they fill all the levels up to a given energy, which we call the Fermi energy. And these typical values of the Fermi energy in metals, for example. In metals, we have these freely moving electrons, which make them conducting. And you can treat these electrons as an almost non-interacting ideal gas, at least in an approximation. And hence they have a Fermi energy which is of the order of a few electron volts, which is 10 to power 4, 10 to power 5 Kelvin. So if you are considering a metal, and a macroscopic metallic object, the room temperature is low temperature. Not 0, but a low temperature. But we first studied what happens at 0 temperature. The first thing we observed, I still think I have a mistake in this 9 over 10. That is not the correct number. Because PV is not 3 over 2U, it is 2 over 3U. You see, even though we are at 0, even though we are at 0 temperature, the gas still exerts a pressure.
There's a G factor in the calculation, so it was the degeneracy.
Yes.
So it's because of the spin, 1 over 2 minus 1.
That is one source, yeah.
But in the boson case, there was nothing like that, as I know.
Well, you can add it still. I mean, probably we ignored it because bosons, we have also spin zero bosons, which have one degeneracy. But yes, at the end of the day, I mean, the adding of that factor is kind of trivial. In the case of fermions, it's definitely there, at least 2.
Yeah, but for bosons,
for bosons, it's also there.
So, for the internal degrees of freedom, should we include the degeneracy each time or just once?
Which degeneracy are we talking about? For example, here, I'm just thinking about a free electron gas. Mm-hmm. There are no internal degrees of freedom. Let's say that you want to talk about, I don't know, helium-3 ion, helium-3 atoms. They are fermions. Then you have an internal degree of freedom. But then due to the internal degree of freedom, there is an additional partition function which you have to take into account. So the partition function gets multiplied by this internal partition function. But you just have to treat it separately. If, I don't know, you don't consider any excitations of helium-3, if you're at sufficiently low energy, then again, it's just a constant number. You can absorb it in this G.
So it corresponds to the electronic degree of freedom, right?
Well, in the case of helium-3, you have the atom, you can excite the electrons, and that's all you can do. You cannot do anything else. But if you have a fermionic molecule, then you also have these vibrational modes, rotational modes. Okay, that is practically where we had left. And today, where we will pick up is if the temperature is low but not zero, like the room temperature. Room temperature for metals is a low temperature but not zero. So what are the corrections? Any questions up to here? Okay, so let me pick up these three equations. Because these equations are valid at any temperature. They are the same equations, whether we are at low temperature or high temperature. We cannot solve them exactly. That is why we are looking at certain limits where we can actually solve them. You see, what we need to do is we need to somehow solve this equation for Z in terms of the N and V, and then substitute it into other equations to obtain the pressure and the energy in terms of the number of particles, the volume, the temperature, etc. Now, low temperature limit Z close to zero is easy because we know the Taylor expansion of F functions. F3 over 2Z is just Z if Z is very small, plus higher order corrections. Now let's see what happens if the temperature is very low. Remember, Z is e to power beta mu. Now we are at low temperature, so mu is close to epsilon Fermi. There will be some corrections. It will be less than epsilon Fermi, but of the same order of magnitude. Beta is much, much larger than 1. So we are actually looking at the case where beta mu is a very large number. And hence, Z is much, much larger than 1. So we cannot do a Taylor expansion in this limit. So we have to come up with new tricks to calculate these functions. Now, what was F nu of Z? This was given by 1 over gamma nu dx from 0 to infinity, x to the power nu minus 1 divided by e to power beta x minus mu beta plus 1. This is our f of z, and we are looking. Now, the first thing we should note is that this function, let me first go back to epsilon. X, I will define it as beta epsilon. It will be intuitively easier. This will be 1 over gamma nu beta to the power nu from 0 to infinity the epsilon to the power nu minus 1 divided by e to power beta epsilon minus mu plus 1. This is what we need to calculate. So here we have integrals of this form. 0 to infinity the epsilon, some function of epsilon. That can be an arbitrary function. In our case, it will be a power of epsilon divided by e to the power beta epsilon minus mu plus 1. Now, if you remember our discussions in the beginning of last hour, we looked at how this function behaves as t goes to 0. And we had said that this function becomes a step function. So still we are not strictly at 0. We would like to calculate corrections to this. So those corrections which we expect to be small, they should be small. So let's separate this contribution. We have this integral. There is a contribution from the step function to this one. Let me try. There is this contribution. If there was actually the step function, the integral wouldn't go to infinity, it would just go up to mu. It's still not the step function though. Plus there is the rest. Now I will now separate the contribution of the step function. Let me rewrite this first in a slightly different form. Now my purpose now is I have this integral. I know that the integrand is more or less like the step function. So I would like to first separate the contribution of the step function at low temperatures. Plus there will be small correction. That's what I'm trying to do. This one over here is the step function. So that contribution now I have separated. This is the contribution from the actual step function. Plus there are other corrections. Well, let me subtract that 1. If I subtract that 1, I get this becomes a minus sign e to power beta epsilon minus mu plus 1 divided by e to power beta epsilon minus mu plus 1 plus mu to infinity the epsilon g of epsilon Yes.
Why did we change from epsilon over v minus 1 to an arbitrary factor of t?
Well, it's a more general function.
That's
That's the only reason. Rather than writing epsilon to the power mu minus 1 all the time, it's just,
not included.
no. I can just choose g epsilon to be epsilon to the power mu minus 1. Now, okay, I have separated the contribution from the step function. It is this one. The rest should be small. Now let me, how to see that those are small? You see, if you look at the second integral, for example, epsilon minus mu is positive within that range, because epsilon, within that integral, epsilon is larger than or equal to mu. It is positive. Since it is positive, beta is very large. Remember, we are looking at t very close to 0, so 1 over t is very large. So that exponent in the denominator, this term over here, within that integration range, is exponentially large. Well, the integral will be small. Well, if you look at the other term, let me rewrite it again, that term also. I just multiply the numerator and the denominator by e to power minus beta epsilon minus mu. Now within that integral, epsilon minus mu is always negative because epsilon is less than mu. So minus times epsilon minus mu is positive. Beta is again huge, so we have the exponent of a huge positive number, which is huge. 1 over that huge number is a very small number. So those two integrals, we can already see that they are small. Well, I still would like to somehow simplify these. You see, one of you had proposed just to say the denominator to x, the exponent to x, not just separate, not just beta epsilon, but beta epsilon minus mu to x. Now let's try that. Because now I can do that. Now let me put this 0. Now this is from mu. Sorry. In this integral, let me call beta epsilon minus mu as x. In the other integral, let me call beta mu minus epsilon as my x. If I do this, the integrands in both integrals will be equal. So let's see, this is equal to 0 to mu the epsilon g of epsilon. Well, here in the epsilon is minus, well, okay, so let me just minus, when epsilon is, from the epsilon I get a 1 over beta. Well, there's an additional minus sign, but I will switch the integration limits. So when epsilon is equal to 0, x is beta mu. When epsilon is equal to mu, x is 0. The x g of, well, epsilon is mu minus x over beta divided by e to power x plus 1. Well, the other integral I will do the same thing, plus when epsilon is equal to mu, the lower limit is 0 up to infinity. The x, I also have 1 over beta. G of epsilon is x mu plus x over beta divided by e to power x plus 1. Now, let's look at that second integral. Mu is of the order of epsilon Fermi. It's not a small number, it's a non-zero positive number. Beta is close to infinity. So the upper limit of that integral, beta mu, is a huge number, typically. So if you, for x huge, well, the integrand is exponentially suppressed, e to the power minus x. If x is huge, I can just ignore the 1 compared to e to the power x. So the integrand is exponentially suppressed, so there's practically no contribution to my integrand from large values of x. So whether the upper limit of my integral is beta mu, which is a huge number, or infinity, it won't make any difference. So this will be 0 to mu the epsilon g epsilon plus 1 over beta, 0 to infinity the x g of mu plus x over beta minus g of mu minus x over beta divided by e to the power x plus 1.
So is u large? No, u is
What is u?
mu.
Mu.
Mu is of order
Epsilon Fermi, yeah.
Right? Not huge. Arbitrary.
Well, I mean, for metals, Fermi energy is something like electron volts. So mu is of the order of 10 to the power 4, 10 to the power 5 Kelvin. At room temperature, beta is just 1 over 10 to the power 2 Kelvin. So beta mu is of the order of 10 to power 2, 10 to power 3.
But your argument would still be valid for beta light, right?
Yes. Yeah, mu is maybe not very large, but beta is very huge. The important thing is mu is not negative and it's not negligibly close, it's not very close to 0. Those are the important things. So that beta mu is large. Well, that is how we define the low temperature limit anyway. Beta mu should be large, effectively. Now, well, you see, if you look at the integrand, you see, we don't know what the function g is, but it will be a polynomial of its argument. That's what we are interested in. It will be x to the power nu plus 1. And that is one thing. Secondly, well, there's nothing that diverges in my integral. The polynomial diverges, but for large values of x, but for large values of x, there is the exponential separation that is always converging. That's something nice about the exponential function. Its integrals are always convergent. So there's no risk of divergence. You see, in the case of bosons, that +1 was a -1, and that led to possible divergences. Because the integrand that would diverge at the limit of the integral. So the integral need not converge. But here, exponent is a positive number, +1 is a positive number. The denominator will never be 0. There is no risk of having a 0 denominator there.
There should be a small amount of correction since we are cheating the integration.
Limit, sure, but the correction is exponentially suppressed. There is an exponentially suppressed correction to this result.
How did we combine the two different x's to be a single x?
Well, you see, x doesn't have any meaning, it's just a dummy variable.
But we said x is one thing, and on the other side of the other integral,
You see,
it should be negative x.
you see, x is never negative. In both of them, x is positive.
No,
One of them is
one of them we said beta mu minus epsilon.
No.
Which, if it's x, then beta epsilon minus mu is the reverse of signs.
You see, I don't really care how I define the x over here. It doesn't matter. Because the definition of this integral is fixed. It's just give values to x, calculate the integrand, and sum them up. That is what that integral is. Well, what does x stand for?
Okay.
Who cares?
Okay. Now it makes sense.
What if we need to do the inverse thing? Which x to be the
Whichever one you want. You see, this is a mathematical expression. What would you like to do with this? In fact, I will integrate it. So I don't even need to go back.
I was going to cover all the possible x's anyway, so
Sure. No, I don't care.
that makes sense.
Except that maybe we cannot use the Taylor expansion in this case, but I guess the numerator can be Taylor expansion.
You see, Taylor expansion of what? Taylor expansion with respect to what? You have to have a small parameter.
So beta is a small parameter, I guess.
Yeah, beta is a huge parameter, and we know that the contribution to this integral is not from very large values of x. The contribution will be from reasonable values of x because of that exponential in the denominator. So x over beta, since x is a reasonable number, not very huge, beta is a huge number, x over beta is a very small number, so I can Taylor expand in x over beta within that integrand. So that is what I will do next. And you see, it will be nice because g of, let's say, mu plus or minus x over beta, this is equal to g of mu plus or minus g prime of mu x over beta plus 1 over 2 g double prime of mu x over beta squared, plus if you want to calculate higher order terms, you can just go ahead. So g of mu plus x over beta minus g of mu minus x over beta. Well, both of them contain g of mu. When I take the difference, g of mu, this term cancels. This term, again, they have the same sign in both of those terms. They also cancel. So I am left with, this is equal to twice x over beta, g prime of mu, plus higher order terms. But these higher order terms are actually of the order of x over beta cubed, not squared. Squares cancel. You see, we are looking at terms for which this typical value of this x over beta will be, let's say, 10 to the power minus 2. Then x over beta cubed will be 10 to the power minus 6. So they will be really small. For example, for metals at room temperature, for the electrons in metals in room temperature. So this gives me, let's see, we started from this integral over here. We had seen that this is approximately equal to 0 to mu d epsilon g epsilon. That is our first term. Plus there are corrections. 2 over beta. Well, there is a 1 over beta over here. There is an x over beta over here. So 2 over beta squared. And g prime, the derivative of this function, whatever that function is, at mu. And then we have the integral, the x over e to power x plus 1 from 0 to infinity. So that integral is gamma 2, 1 over gamma 2, 0 to infinity, the x to the power 2 minus 1 divided by 1 inverse e to the power x plus 1. The reason why I write it in this fancy form is this function is what we call f2 of 1. Now, so this integral, the x over e to the power x plus 1 is gamma 2 is just 1. This is f2 of 1. So this is what we have. Plus 2 beta squared, no, 2 over beta squared, g prime of mu, f2 of 1. Plus other corrections. So any questions up to here? This is what we will study. We would like to calculate the force.
We had gamma 2 function.
Gamma 2 is 1. That is 1. Now let's remember one result we had derived about these weird f functions on Monday. If I can find it. Yes. This is one thing we had derived. G functions are the functions we know from the boson. So F2 of 1 is G2 of 1 minus 1 over 2 G2 of 1. Well, Z is equal to 1 is nice because Z squared is also 1. So this is 1/2 G2 of 1. This is 1 over 2 Riemann zeta function at 2. You see, no, so G2 of 1. Remember, G nu of 1 was given by 1 over n to the power nu, and from 1 to infinity, which is nothing but the Riemann zeta function evaluated at nu. Well, this Riemann zeta function has its values tabulated, so zeta 2 is pi squared over 6. And if we go back, so now we have an approximation of this integral. This is pi squared over 12. So these two cancel, 6. This is approximately 0 to mu d epsilon g epsilon plus pi squared kt squared over 6 g prime of mu plus higher order terms. So any questions up to here? Yes, okay, there are some technical steps, but the basic idea is still there. We are basically replacing the Fermi-Dirac distribution by a step function plus corrections. The first integral over there is what we would get from the step function. The correction will be small because at low temperatures, we already had seen that the Fermi-Dirac distribution, if this is the Fermi level, it will look like something like this. It will be 1 up to some energy values close to the Fermi energy, and basically 0 above energy levels, slightly above the Fermi energy. In fact, even if we had just approximated this function by such a step function somehow, we would probably get more or less the same answer, numerically speaking. Now, of course, once we have this, now we should use it to calculate what we would like to do. First thing to do is always, what is the chemical potential as a function of temperature? You see, we know that mu, when T is close to 0, will be epsilon Fermi plus some corrections. So what are those corrections? That is the first question. Now, to calculate that, we know how the Z is related to temperature and the density, and lambda cubed over G is F3 over 2Z. Now, this F3 over 2Z, we had already wrote it in a slightly different form. I will just insert the, let me insert the definition first. This is 1 over gamma 3 over 2 d epsilon dx x to the power 1 over 2 divided by e to the power beta epsilon minus mu plus 1. This is the definition of f3 over 2 of z. Oh, sorry, this is e to the power x minus beta mu. We make the change of variable, x is equal to beta epsilon. So this just gives me 1 over gamma 3 over 2 beta to the power 3 over 2. The epsilon over e to the power beta epsilon minus mu plus 1. You see, in this expression, now this is 1 over 2. G of mu is square root of mu. G prime of mu is 1 over 2 square root of mu. So now I can just use this expression, this approximation. This is approximately equal to 1 over gamma 3 over 2 beta to the power 3 over 2. The integral from 0 to mu of the epsilon square root of epsilon, well, plus this term g prime of mu, which is 1 over 2 square root of mu. So n lambda cubed over g should be equal to 1 over gamma 3 over 2 beta to the power 3 over 2. The first integral just gives me mu to the power 3 over 2 times 2/3. This is the first integral. Well, the second integral is pi squared over 6 kt squared 1 over 2 square root of mu. Well, let me take the first term out. Two-thirds mu to the power 3 over 2, 1 plus pi squared over 4, pi squared over 8. Kt over mu squared, plus, of course, higher order terms.
Is beta 3 over 2?
3 over 2. Yes. Well, if you just ignore this term, what remains just gives us the Fermi energy. So in fact, n lambda cubed over g is equal to 1 over gamma 3 over 2 beta to the power 3 over, sorry. No. Well, let me leave it over here. The one term does give me the Fermi energy, but you see, if I put t equal to 0, lambda diverges the right-hand side, both sides diverge because both sides are proportional to 1 over t to the power 3 halves. Let me just put it there. So n lambda cubed over g, this is 1 over gamma 3 over 2, beta to the power 3 over 2, 2/3 epsilon Fermi to the power 3 halves. This is the definition of Fermi energy. Well, to get rid of all those n's and lambdas, all those weird factors, let me just divide them side by side. So 1 is equal to mu over epsilon Fermi to the power 3 over 2, 1 plus pi squared over 8 kt over mu squared. I have to solve this equation. Well, I will basically use the same trick. Well, let me also write the second term in a slightly different form. Kt over epsilon Fermi squared times mu over epsilon Fermi to the power minus 2. I'm basically writing the same equation.
How do we go from square root of mu to mu squared?
Where?
On the arrow part.
Here.
At the term you draw. Yeah, from there to the.
You see, I just took this out.
Okay, but on the second term we didn't multiply with anything, but still we went from 1 over square root of mu to 1 over mu squared.
But you see, I'm taking out square root of mu cubed. This term is.
Ah, you took one from the. Okay.
I took that out. So in the second term, I obtained square root of mu to the power 4. That's mu squared.
I missed.
Well, let's solve this equation and give a break after that. Yes, I already know mu over epsilon Fermi is 1 at t equal to 0. And I would like to calculate a correction to that. Well, the solution will be a function of kt over epsilon Fermi squared. So if I imagine a Taylor expansion, it will be a Taylor expansion in kt over epsilon Fermi squared, not kt over epsilon Fermi. And let me assume that the coefficient is delta. So 1 is, if I take the cube root, no, the 3/3 power of that expression, that will give me 1 plus 3/2 delta kt over epsilon Fermi squared, 1 plus pi squared over 8 kt over epsilon Fermi squared, plus terms of the order of kt over epsilon Fermi to the power 4. Well, now you might ask how I could ignore mu over epsilon Fermi to the power minus 1. Well, you see that factor is 1 plus something of the order of kt over epsilon Fermi squared, but that is a multiply by that factor in front. That gives me a correction of the order of k2 over epsilon Fermi to the 4th power. Those I am ignoring. I'm just looking at the first correction to mu over epsilon Fermi. And let me open up this parenthesis. This is 1 plus pi squared over 8 kt over epsilon Fermi squared plus 3/2 delta kt over epsilon Fermi squared plus terms of the order of kt over epsilon Fermi to the 4, which tells me that pi squared over 8 plus 3/2 delta should be 0, or delta is equal to minus pi squared over 12. So the chemical potential is epsilon Fermi 1 minus pi squared over 12 times kt over epsilon Fermi squared plus higher order terms. You see, we had already said that if we increase at t equal to 0, the chemical potential is epsilon Fermi. If we increase the temperature, it should get smaller and smaller. Well, that is why we have that minus sign. That this result is something we expected. So there are corrections, negative corrections at finite temperature. So the next task we will do is, okay, now we know the chemical potential as a function of temperature. So what about, let's say, the pressure? What is the pressure of this system? What is the energy of this system? Now let's give a break. Any questions before the break? Okay, so see you in 10 minutes.